An interesting concept that helps you understand the various designs of pumps is specific speed. Now, this doesn't refer directly to the rotating speed of a pump. It is a factor in it, though. And the equation for specific speed of a pump is specific speed equals RPM times US gallon per minute to the half power divided by head to the three-quarter power. Um, we're US gallon per minute. We've used that because most of the information I've got has been based on US units. Now, another definition of specific speed is the RPM at which a geometrically similar pump to that under consideration but reduced in size, like a model, would run in order to produce 1 gallon per minute at 1 foot head. Now, what does that really mean? When you start looking at pumps and the specific speeds, uh, specific speed below about 2000 is considered centrifugal flow or radial. In other words, the water comes in and virtually makes a right angle and discharges off to the sides. Okay, now, and here, if you look at this graph to the right, it shows you what that looks like. In other words, it's virtually a straight right angle discharge, and it shows you the head efficiency and power that is typical of that pump range. Now, moving up to between about 2000 and 5000, you get into turbine or Francis type pumps, where it's an angled discharge. Not super dramatic, but still. And again, if you look at the chart on the right, the middle two, you can see that we're discharging at a bit of an angle, but not straight out and certainly not straight back. Specific speeds between 4,000 and 10,000 indicate mixed flow like drainage pumps, where there is some angle to it coming off, but not a whole lot. And finally, between 9,000 and 15,000, we talk drainage pumps, axial flow. Literally, the impeller is like a propeller in the fluid. There is not much of any radial action at all. Now, interesting, here's a plot of the typical efficiencies that you can expect with different specific speeds. The one thing you will notice is that mixed flow designs, in fact, around 2300 is the most efficient design. So which is basically, again, as we said, a Francis type design. Keep that in mind because it will come back. Now, different ways of doing an impeller. We're talking an end suction single stage pump here. The classic is a closed impeller. There's a shroud on the front of the vanes and a shroud on the back of the vanes. And recirculation from the high pressure discharge back to the inlet is minimized, controlled by a set of wear rings, which means a tight radial clearance, almost like bearings on a car, except the clearance is fairly tight, and that causes a major restriction to flow coming back. Now, again, if we want to balance the axial thrust, then we put a second wear ring on the back. You can see the back red line at the bottom of it. Again, there's a horizontal wear ring shown there. And we put in bleed holes so that the red at the bottom there, the red ring, wear ring, actually drops. It causes a pressure break. And with those bleed holes below that, we have inlet pressure above that discharge. So basically, in terms of thrust, the impeller is pretty much balanced out. Next up is a semi-open impeller, which has a shroud on the back only. Recirculation from the discharge back to the inlet at the front of the impeller is controlled by having a very close tolerance between the impeller and the casing. So that has to be adjusted fairly close to end up with a reasonably efficient pump. Axial thrust is increased over other designs because there is that pressure drop on the front that isn't seen on the back of it. Discharge pressure is full on the back of the thing. There's a couple of things about semi-open impellers. They're great for handling small solids because of the action of the casing relative to the inside of the impeller. And they do have good efficiency as a rule, a general rule, because the impeller can be cast and machined fairly easily. Then we go to a full open impeller, which basically is like a semi-open impeller, but with only a minimal shroud at the back. So essentially the pressures will balance on both sides. Now in that case, you have to have not only a tight clearance on the front, but a fairly tight uh, clearance on the back as well. The efficiencies because of this are a little bit lower than other impeller designs, but they're often used in the chemical industry because, again, they're very good at handling small solids. And as we say, it has virtually no thrust. Now, looking at the volute itself in detail, you can see a typical casing. You can see the cutwater, the point at which flow is diverted off from the face of the impeller. And you can see how the casing, actually the area increases as it goes around, which causes not only picks up water but causes the flow rate to slow. Um, One of the interesting things about this is the closeness of the cutwater. If the to the veins of the impeller, if it's really close and you have few veins, then you're going to get noise. It's just inherent in the animal. And the classic worst example of this is self-priming sewage pumps, which only have typically two veins and have to be close to the cutwater to work properly. In fact, that clearance there is so important that in commercial high-rise buildings where you have multi-vane pumps, which helps with the quiet, they still typically specify that the impeller be trimmed to be equal or less than 80% from the shaft center line to the cutwater distance. That means that the impeller vanes are away from the cutwater. You don't get that pressure off the tip of the impeller whacking against that cutwater, and the pumps are much quieter. Now, we did talk about diffuser types pumps where the circumference as you move away from the impeller gets larger and larger, and you can see there's actually guide vanes on the diffuser to pick up the flow. And as it moves out, of course, the water is slowed down, the pressure or head, same difference, rise. And again, as we said before, typically we don't use a single discharge at one spot. They're usually discharged all around, tapered back to the next stage, and are typically used in multi-vertical turbine pumps being the classic ones. Efficiency. A very significant consideration nowadays is the overall operating efficiency because electric power costs are significant, uh, and not only in terms of cost, which makes the cost of the pump seem less and less important, but of course the environmental green effects of reducing energy consumption. At one time, overall pump efficiencies were relatively high, but then everybody got off on low equipment cost. Well, one way of making low equipment cost, reduce the cost of the pump, uh, is to make things a little tighter, et cetera, and efficiencies dropped. Nowadays, that pump efficiency is becoming, again, a very big factor. They're going back to the future and pattern to a lot. If you're already building a pump, it costs a lot to have the castings for a new pump, but it's you're seeing that trend in that direction. So everything old is new again. Um, and it's the overall efficiency range you'll be operating in that is more important than the actual peak pump efficiency alone. And there are times when system performance serviceability considerations have to override efficiency. It's a great pump, maybe very efficient, but if it has problems, it usually ain't worth it. One of the things I put together was the concept of amortized operating cost. And you can see there's an equation here which basically, as you can see, required to offer three different pumping equipment options and the cost implications. And included in that would be the amortized operating cost, where a specified liter per second or US gallon, whatever, specified TDH in meters. And if you've got two duty points, then the average between them. Um, and a constant derived from standard power calculation plus 8,800 hours of operation per year and power cost, as you can see there, 0.07 cents per kilowatt hour. One of the nice things about that constant 6.03 is you can play with this. And this was put in on tenders, and the contractors had to provide this. And basically, you get to the point where you can kind of balance that constant out so that you're getting reasonable answers. In other words, that you're not paying the moon to get efficiency, but it is a significant factor. And along with that was the thing that actual delivered flow rate, no penalty for providing more flow, and et cetera, et cetera, et cetera. One of the things, and you can read this, one of the things, Hydraulic Institute acceptance level A or B, minimum efficiency tolerance, will be applied. What that means is you can look at a pump curve and it'll tell you what the efficiencies according to the manufacturer are. But we do require, and that's a subject right there, factory testing. An unwitnessed test is an excellent idea. Then you know exactly what the pump you've got is doing. Do we trust the manufacturers? Yes. They would be in real trouble if they were caught cheating on this thing. They'd be out of Hydraulic Institute. So a non-witness per hydraulic standard, and you got two choices there, A and B. And you can see as you follow down, head shall be at the lower end and gallon per minute, plus 8%, no minus tolerance allowed. Design capacity for A, no minimum allowed. B is a little more generous, allows 3, and you can kind of follow down. Let's pick one at design capacity. Head shell being is between 2 and 500 feet, plus 5. In other words, if the pump puts out more heads, so be it, not a problem. No negative. It has to meet that deal. Where B does under A, but where B does allow you some variation. So generally speaking, A is the way to go. Minimum efficiency at rated capacity at total head, and contract efficiency, as you can see, there's a little formula for arriving at that. Okay? Now, one of the interesting things we talked about was speed. And people tend to assume that a lower rotational speed will provide better efficiency and longer pump life. But in fact, efficiency is related to pump-specific speed. Remember, around 2,000 to 5,000 is where you're most efficient in pump designs. Often better efficiency can be obtained by a pump that operates at 2-pole motor speed, 3,600 RPM less slip. We'll get into that in much detail later, rather than some lower rate. Pump bearing life is dependent upon the mechanical design of the specific unit. Of interest, you tend to think that a 4-pole motor speed or lower, in other words, 1,800 RPM, it will seem quieter due to the lower frequencies involved and the fact that the cooling flow through the motor is less. And the impact if a big rock gets in there obviously is going to be less if it hits the impeller. Now, there are geared centrifugal pumps out there that typically operate between around 13,000 to 32,000 RPM. And here's an example of one, the little green pump. And you can see the size of it. At the back of it is where it mounts onto the motor. And inside there is a great big gear that is driven by a 2-pole motor. In other words, 3,600 slightly under. And where you see the little, almost looks like a toy impeller in bronze, the impeller in that thing is driven by a small gear. So that thing screams. And this particular pump is capable of up to 33 gallon per minute, not much, heads up to 1,300 feet. Okay, now that concept, and actually this is where the idea originally came from, was the V2 rocket, which had a very high speed impeller. And here's a typical one. This is out of a Titan II missile, which had hypergolic fuel and oxidizer. Basically, what that meant, hypergolic, by the way, they didn't need to ignite it. As soon as the chemicals touched, it went. And that fuel was, there it is, an oxidizer, there again. But the pumps that were moving that stuff, traveling, as it says here, about 9,000 RPM. And I should throw in a plug for the Titan Missile Museum just out of Tucson. It is worth a visit if you're ever in that area, as is Pima Aerospace. Now, bearing frames. every pump will have a fixed bearing and a floating bearing because shaft thermal expansion and contraction occurs. And inevitably, the fixed bearing is at the back, and so that the shaft variation has no variation on what's being driven at the end, and a floating bearing in between. That bearing, where the back one is held in with clips, the front bearing there between the output shaft and the impeller, that front bearing can move forward and aft. It's tied to the shaft, it can move within the casing as that shaft expands and contracts. Sealing. You've got a shaft that's turning and a case that isn't. So between the two of them, the classic way of doing it was to put in packing. Packing is basically, in the day, was asbestos rope with graphite on it. For reasons, as you well know, asbestos is no longer used. So now it's synthetics, Teflon being one of them that is used to make up the ropes, and we'll get into that further on as well. And that basically is compressed by a gland, which two or more nuts are tightened to compress that rope, the packing, so that it rides on the shaft to some extent and seals at the top at the casing as well. You can see where pressure would try to get through and can't. Now, not uncommon to have a lantern ring in the middle, and there's games you can play if you have a lantern ring in there. You can use it to break off pressure or to put in a flushing fluid if you want. And again, we'll get into that. Okay. Looking at the parts, there's the gland follower, which is used, you can see the lines on it, is usually split so you don't have to take it off the end of the shaft, take the pump apart. You can just pull it apart and there it is. And back in the days when they used asbestos and graphite, you usually have to count on about a drip a minute. If you tightened it too much, you would burn the shaft. Nowadays, with using synthetic packing, you can virtually get to almost dry. And although you can get pre-molded rings of packing, the classic way to do it is simply take a packing off a spool, wrap it around the shaft, and cut at one point. You can see that cut line right in the middle there. And that will give you a bunch of packing rings just about all set to go. And we talk about the lantern ring, as I said, can be used to introduce a clean fluid to prevent dirty fluid from entering, or ensure that air is not drawn into the pump under negative pressure by having a flush pump. One of the common things to do is simply take the discharge of the pump and tie it into the lantern ring, because then the packing is always pressure and no air can be drawn in. It can also be used as a bleed point to reduce the pressure on the outer part of the packing. And again, you can reduce leakage quite a bit. If you don't have a lantern ring, classically one more ring of packing is provided to provide the pump seal. It's simple, allows the shaft to move in and out, but it is somewhat maintenance intensive. It goes and is usually put over a renewable hardened shaft sleeve because it does tend to wear that. And with a renewable sleeve, you can pop the sleeve off when it's worn, put it back. And the red here is typical specification of what's involved. And if you've got a vent lines coming off the discharge, it specifies a little glow valve for throttling it, etc., etc., etc. Now, mechanical seals. What is the magic of mechanical seals? Basically what it is, they have a stationary face on this drawing, it's blue, and a rotating face, which is orange. And the two faces, the stationary face and the rotating face, the stationary face, by the way, is held to the casing with seals, okay? There's different ways of doing that, O-rings, whatever, but basically it is sealed. And the rotating face is pushed by a spring, and you can see there's a piece at the back. That little gray thing would be a set screw go in to hold that so it spins. The faces are lapped and polished to about 2 light bands. That's the way they're described, as 2 light bands flatness, which is 0.6 of a micron, or millimeter, inches. 1.2 inches to the power 10 to the minus 5. Do your decimal point out. Many assume these seals are leak-free. They appear that way, but there in fact is a little bit of leakage, like maybe half a teaspoon a day, through that thing, except you never see it because it just vaporizes off. Now there's umpteen different types of mechanical seal. The classic one is an unbalanced inside seal, okay, which has the pusher spring, which helps push the two faces together, plus pressure. If you follow this thing through, pressure will, from the pump side to the left, impeller side, will actually tend to push the two faces together. And that's, most of the time, that's fine. By the way, your car has a mechanical seal in it. That pushing together is fine to a point, but it can be too much if you're dealing with very high pressures. So we have balanced inside. Inside means most of the seal is on the inside towards the impeller. So a balanced seal has a little step so that if you look at the thing where there's all those little arrows, the pressure is almost independent, or the pressure on the faces, contact pressure, is almost independent of what the pump discharge pressure is. The pressure required is being provided by the spring. Now, another option is a balanced outside seal, which has a pusher spring and is designed in such a way that, again, the hydraulic forces are equalized. Why have it outside? Because it avoids garbage getting caught on the spring, like on a sewage pump or something like that. And it's easy to work on, to inspect, okay? Tandem seals. A lot of submersible sewage pumps use tandem seals. Both are the same way. They're essentially unbalanced inside mechanical seals, a lower one and an upper one. The lower seal is actually, the spring and everything are actually outside the chamber. The upper seal is in a bath of oil. And as I say, commonly used on submersible pumps. The oil, by the way, is transformer oil. At one time, back-to-back, particularly on dry pit pumps, back-to-back, which you'll get into later, back-to-back seals have two seals oriented back-to-back, so the pressure in between is pushing both of them. It has the advantage that the seals are operating in the flushing fluid, the fluid in between, so the springs aren't actually where there is any raw sewage. Nowadays, you don't see them as much because inside mechanical seals have got to the point where they can pretty much handle anything that's needed. For example, here is a mechanical seal specification. A couple of brands listed, as we mentioned before. That way it's there. An external flush line, etc., etc., etc. You can kind of follow through that spec as you want. Now, cartridge mechanical seals is typically an inside seal, balanced or unbalanced, but with the rotating components mounted onto a sleeve that is attached to the pump shaft by a collar with set screw. And you can see that like at the outside there to your left. You can see where there's places for a set screw, okay? The advantage of doing that is on a vertical turbine pump where you have to, on occasion, adjust the impellers, which means moving the shaft up and down, and the mechanical seal would be destroyed, and I've seen it happen. Mechanical seal would be destroyed if it isn't separated from that action. So with this particular thing here, if you have to move the shaft, what you do, put in, you see these little red collar things which hold it. Then you can hold the seal to the sleeve, the outside part of the seal to the sleeve. Then you can undo the set screws, move the shaft. When you're happy with what you got, tighten up those set screws, and then remove those plastic pieces and put them on a shelf someplace, okay? The throttle bushing here, by the way, there's the inside seal. This bellows is used as a spring. Da-da-da-da-da. There's your contact points, okay? And you can put in a flush. You notice here, what is this? It's called a throttle bushing. And what that means, if that seal should fail, you won't get huge flows. It'll be restricted by this throttle bushing. And if you want, you can put a pressure in between here, some sort of fluid, and use that as flushing because this acts as an outer restriction, okay? And there's your centering tabs, and very, very interesting approach. And I went through that thing with vertical turbines, and here's a specification for it all. And always have a lamicoid, as it specifies here, saying, "Warning, affix seal tabs and release sleeve before adjusting shaft." Mechanical seals are virtually leak and maintenance free, but must never be operated drive, as their life is then measured in seconds. And I know from hard experience, uh, if you run a mechanical seal absolutely dry, they will destroy themselves fairly quickly. Motor sizing. Um, we do have later on we'll get into motors and generators. And we'll get into the fact of how the base for a pump is installed, which is very important. And here we have a typical specification which calls for factory testing. In this case, as we recommended, acceptance level A, da 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 da, and hydraulic vibration, which is tied down by Hydraulic Institute. And again, the requirement that the contractor and his supplier have to meet Hydraulic Institute standards for vibration. Inlet design. Where dry mounted pumps are involved, the inlet line should be sized for a minimum velocity of about 2 feet per second and a maximum velocity of about 8.2. The minimum velocity particularly applies to sewage pumps to keep stuff in suspension, okay? And important to prevent air pockets at the top of inlet lines. Therefore, any reducers on horizontal should be eccentric rather than concentric. The left, you can see it's right along the top. There's no place where air can trap. On the left, you've got a drop in the size of it. That's where air can form, and you can run into some problems. Now, getting into inlet design, odd as it may seem, pumps seem to work better with turbulent inlet flow. Therefore, a standard reducer fitting right at the pump inlet is advisable. Now, this is kind of neat. This is the actual inlet to an F-111 jet, and you notice the little tabs all around. You see them on wings of aircraft. Those generate turbulence. And basically, that's what they're doing, is generating turbulence because they don't want laminar flow into the inlet of the engine. They want it to be mixed a little bit. And same thing with pumps. That is an important thing to make sure that it, oddly enough, is not too smooth. We'll get into that later. Double suction pumps must not have any close inlet elbows in the horizontal plane, or this will cause one side of the impeller to be significantly loaded more than another. And I saw a classic example where it wasn't a 90-degree bend. Believe it or not, it was a 180. And the thrust bearing on that pump was not a happy camper. It got really, really hot. Okay, so that's the end of that section, and I appreciate your patience.